Okay, good morning. So we continue the lesson of combinatorics. If you remember, we started talking about the product principle. So if we have a task that can be accomplished in 2 stages, and if you can do the first stage in, say, n ways, and when this first stage is accomplished in one of these ways, the second stage, independent of how the first stage is done, can be done in n ways. Then if you want to do the task, you have n times m different ways to do it, yes? So now we want to generalize it for actually more than one, more than 2 stages. So if assume that you have a task, let me just tell it for 3, and then you can generalize it for more yourself. So assume that you have a task. You have a task that can be accomplished in 3 stages now, rather than 2. And then the first stage can be done in n1 ways. And when the first stage is accomplished in one of these n ways, okay, so how should I formulate it? The second stage can be done in n2 ways, independent of how the first stage is done. Yes? And then after the first and second stages are accomplished in one of these ways, then the third one, the third stage, independent of how the first and the second one are done, can be done in n3 ways. Then for doing the task, we have n1 times n2 times n3 tasks, yes? So the second one should be independent of how the first one is done, but the third one should be independent of how the first and the second one are done, yes? Of course, it is easy to generalize it. So here, I have written the most general form, but it is very lengthy. But if you want to say it for a task which can be broken down into k stages, then you have to write so many words. But this is in principle extremely simple to understand, yes? So let us, for example, repeat this if there are 4 stages to be done. So the first one can be done in n1 ways. The second one, independent of how this one is done, can be done in n2. And the third one, independent of the first 2, can be done in n3. And then the last one, independent of the first 3, can be done in n4 ways. Then in total, we have these many ways to do it, yes? So that is just a very immediate extension of what we have, what we had. Okay, so let me try to solve some problems today together using this idea. Okay, and then I hope that you realize immediately that the questions that we answer are not that trivial, even though they are very simple to formulate. But if you don't want to use this as a systematic way, then it becomes a little bit hard to answer. Okay, so for example, let us try to work on this problem. So consider the numbers 1, 2, 3, 4, up to 7 as the only options available. And then we ask how many 3-digit numbers without repeated digits can be written. If you think a little bit about this problem, the answer is not that easy. I mean, it's not that immediately clear what the answer is, yes? Because the options that I have are only these choices, and then I want to count the number of 3-digit numbers without repeated digits that are using only these as digits. So I hope that you agree. This is not asking you how many 2-digit numbers are there. Even if you don't count, you can immediately say 90, yes? This is already a little bit, not hard, but already non-trivial question. You cannot immediately answer that unless you really calculate it. Okay, so let us review. For example, let me just write it here on the board. So the digits that I have, let me write all of them, be patient. So 1, 2, 3, 4, 5, and 6, and 7. So these are the digits I am allowed to use, and I want to write 3-digit numbers. Okay, So instead of writing it, so you need to remember all the time. So you need to train your brain to think in this way if you want to be successful in solving a combinatorial problem. So you need to define the task in your head. So what is the task? The task is to write a 3-digit number. I am not allowed to repeat the digits, and I am allowed only to use these numbers as digits. So this is the task that you have in mind. But hopefully you realize that this can't. If I ask you write a number with that property, this is extremely simple problem. Everyone can do it. So for example, 1, 2, 3, is it acceptable? So this is an acceptable one. It should be counted here. For example, 355, is this acceptable?
No.
According to the condition of the problem, this is not acceptable, yes? So it is a very simple task to write that, but exactly what I'm saying is that if you can write it, in principle, if you analyze it a little bit, you can also count it. So when I wrote 123, you can think in this way that my brain decided about 3 tasks, 3 stages, deciding about this digit, deciding about this digit, and deciding about this digit. So if I want to make the story short, so I would say that it is a good idea, instead of writing so many things, you can write here, I have a task that can be accomplished in 3 stages. Okay, we have some experience from the previous lesson. Sometimes the order of stages matters, actually. Sometimes you can, by rearranging the order, you can solve a problem which you were not able to solve, yes? But I don't think there is some strange thing going on here. So if you don't mind, let me start the stage 1 to be this one. So this S I call for a stage. Stage 2, stage 3. Let us see if it works or not. So this is part A problem. So how many options are available for just doing a stage 1? 7. I can choose one. Yes? But then I go to a stage. So it means you need to think in this way. Assume that the stage 1 is accomplished. What does it mean? It means that you chose one of these numbers, that you had 7 options, and put one of them here. I don't mean I put 7 here. I had 7 options. This is the number of options that I have for stage 1. So the stage 1 is accomplished. I go to stage 2. So how many options are left for me? According to the condition of the problem, I'm not allowed to repeat a digit. So how many options are there?
6.
So this 6, you have to be careful. You need to ask yourself, is this number that I put here is independent of the way that I did the first stage or not? Yes?
Isn't it 7 because it's here?
No, I am just only allowed to use these digits. Yes? So how many options are here? 6. Is this 6 independent of how I did the first stage? I would say yes. For example, in the first stage, it might happen that you have chosen 1. Okay? So you're not allowed to choose 1 anymore, but how many options are left for you?
6.
6. It might be possible that you have chosen 2. Of course, the numbers that are left for you are different from the previous choice, but the number of choices left is again 6. So the number 6 that I put here, I hope that you can convince yourself is independent of which one I have chosen for the first stage. Yes? So that is why this is, so far it is good. But then I go to the third stage. How many options are available for me?
5.
5. And then again, when you want to write 5, you have to be even more careful. You have to check this number is not only independent from the first one, but also independent from how the second one is done. So the first one, I have done it. I have chose one number, for example. In the second stage, I have chosen another number. And then, for example, I can cross it over. Let me write it here. Okay, and then when I reach here, how many options are left? 5. Do you agree this 5 is independent of which ones I have chosen for the previous one? Of course, it will affect my choice there. But that doesn't matter. The matter is the number of choices left for me, which is always 5. Is that right? Okay, and then, so the answer, it means that the product rule is, the product principle is applicable, and the answer is 210. By the way, if you know Python or any language, that is a very good exercise to generate this list by writing a code and count all of them, to confirm that this is exactly 210. So you need to know how to write a code so that it will generate all possible numbers, 3-digit numbers with these digits without having any digit repeated. And then of course that is a very simple task, and then you count it, so you can ask, the length of the list or whatever, then you have to generate 210. So that's a good exercise, by the way. But I hope that you agree, even though this question was very simple to formulate, it was not that trivial that there are 210. So if you don't believe it, you have to start writing them down, yes? Okay, now let us go to the second part. Answer part A, if the repeated digits is allowed, is if repeating digits is allowed, okay? Okay, anyway. But that is, again, very simple. So part B, you immediately can answer that yes. So what happens, again, I have 3 stages, stage 1, stage 2, stage 3. I really didn't have to change the order, so I kept the natural order because it worked. So hopefully it will also work here. So how many options I have here? 7. This is done in one of these 7 ways, and then how many options are left for me? 7, because now I am allowed to repeat, and then 7. So this is 7 to the power of 3, it becomes 340. Okay, part C, how many 3-digit odd numbers can be written if the repetition of digits is not allowed? Okay, so we want to have odd numbers. Okay, repetition is also not allowed. Okay, so if you want to have odd numbers, so do you remember the rule of thumb that I told you? So it is better to take the first stage to be the one with more restrictions on it. Yes. So here I would prefer, because for a number to be even or odd, this digit, it does not decide about it. This digit will decide about it. So this, I cannot put any one of these numbers here. So it means that I have more limitations here than the other two. So this is why, as a rule of thumb, I really advise you to start with this one as a stage 1, even though it's not a natural order of writing a number. By the way, somehow it's natural order, because if I ask you to write an odd number on the board, you already decide probably on the right-hand side to put something, I don't know. But anyway, this is not a natural order if that's not, but in combinatorics, we start from here. And then between these two, probably I do not have any priority. So for example, you can call this one as 2, this one as 3. Let us see if it works. So is that clear? So I decided to start from here because I have more restrictions here. Okay, I want to write an odd number, yes? So I want to write an odd number. So how many options are available for me if I want to put here?
4.
I have 1 here, 1 here, 1 here, and 1 here. So I have 4 options to put here. But now you need to think in this way. Now assume that the first stage is done in one of these ways. The repetition is not allowed. For example, assume that 3 has chosen. Okay? So, and then I want to go to stage 2. How many options are available? The reason that I take it off because of the problem. It is mentioned that the repetition is not allowed. Okay, so how many options are left for me for stage 2?
6.
6. Is this 6 that you write here independent of how I have done the first one? You see that I could have chosen 5. But it will affect the choices I have, but it will not affect the number of choices that I have. Yes? So that is 6. And then hopefully you can convince me it is really independent of my choice. Okay, and now what is left here? 5. Yes? And this 5 is again independent of how I have done the first stage and the second stage. So independency is valid here, so it means that it is applicable. And then I multiply them. What is answer? What's the answer? 120. So there are 120 of these numbers. In principle, you can write a code to confirm all of them. Is it reasonable that because you know that the total were 210, but 120 of them are odd? Is it reasonable? Because it's more than half of them. Why? Yes?
Because in the sequence 1 to 7 there are more odd numbers.
More odd numbers, yes? So the number of evens are 2, 4, and 6. So it is reasonable to have more odd numbers than even numbers, okay? I'm just trying to see that if it makes sense. Okay, part D of the problem is the same problem, yes? No, you want to write even numbers can be written if the repetition of digits is not allowed. So, okay, you can answer this question in a slightly different way now. So what is the answer now? Because we know that in total, without repetition of digits, there are 210. Without repetition of digits, 120 of them are odd. So then, subtract them. So that's another principle, is a complement principle. So the answer is, 90. So you expect to have 90 if every calculation is reasonably consistent. But I don't want to solve it using this rule, which is the complement rule. Of course, you can do it in the exam. That's reasonably correct. But let me just do this again with the product rule directly. So again, based on your experience, which one you take as the first stage? The last one here. So let me take this one as stage 1, stage 2, stage 3. And then for stage 1, I want to have an even number. So let me take them off. So how many even numbers are there? Only 3 of them. So I have only 3 options here. And then one of them is being used here, and I'm not allowed to use it again. So I take it off. How many options are available here? I have 6. And then for the same reason, 5. I always want you to recheck it, especially for the first problems, but the explanations are the same. So all of them are independent from the previous stages. So if you multiply them, your answer, which you predict was correct, 6 times 5 times 3 is exactly 90. Yes, so that's a very simple problem to understand what's going on. Is that clear? Okay. We go back now to the slides and then try to solve this problem, problem 11. Example 11. So in how many ways can 4 persons be seated in a row of chairs in the saloon of a cinema consisting of 30 chairs numbered from 1 to 30? Yes? So you have, I don't know, you have a saloon consisting of 30 chairs numbered from 1 to 30. When I say numbered, it means they are distinct chairs, so they are different. And then we have only 4 people, okay? So the movie is probably not that good, okay? We want to sit somewhere there. And then how many ways we can do that? Okay? Okay, so again, this is a simple problem, but I want to talk a little bit about what is going on here. So what is your take on about it? So the problem is clear. You go into a room. In that room, there are chairs numbered from 1 to 30, and then you're only 4, okay? There is no restrictions if you want to sit next to each other or not. Forget about all these things. You have complete freedom to choose. Then how many ways you can do that? Yes.
So would it be 30 times 29 times 28 times 28 times 20 times 27?
7. Yes, because what is the task? The task is clear. Just what is the problem describing? And then this task can be broken down into 4 stages. Yes, because as soon that you want the task to be done, what does it mean? You want these people sit somewhere, yes? This is your task. And then this task is accomplished in 4 stages. For example, you can assign a seat for the first person. After this is done, you go on to the second person and then ask that person to sit where. So I mean that this task can be broken down into 4 stages, yes? Again, in your principle, in your brain, so you can say stage I, means the ith person be seated, yes? Be seated. Okay, let me write. So for example, we can say that I have stage 1 and I have stage 1, stage 2, stage 3, stage 4. So stage 1 is I want to have the first person be seated. How many options I have to give to the first person to take a seat, yes? How many options? 30, because there are 30 chairs. Yes? But then this person, now I told you that, assume that the first stage is done in one of the ways. What does it mean? It means that you call the first person and say, for example, go and take the seat number 5. Okay? And now you reach to the second person. How many options are available for that person? 29. Again, when you want to write 29, you have to think about, is this number that you put here is independent of how I have done the first stage? It is, yes. Of course, it will affect my choices, which seats are, because if the person is taking number 5, of course number 5 is occupied. I cannot give number 5 to that person. But it doesn't matter, because we are interested in the total number. So whatever this person has taken, there are 29 seats available for the second one. And whatever these people have chosen, how many seats are available for the third one? 28. And then for the next one is 27. And because this independency works, so the answer is, as Rocco mentioned, is just this number, 30. And this is enough for writing in the exam. So you really don't need to multiply these numbers, because multiplication is not just a hard thing to do. Yes? Okay, let me change the problem, and I ask you this question. I don't know, for human brains it seems a little bit different. So assume that now you are 30 people, but then you go into a room with only 4 chairs. Okay, of course, this is not possible that you can give chair to everyone. But how can you just take 4 of them and put them on these chairs? So this time I have 30 people, but I have only 4 chairs. And then what we want to do, we want to give, I need to choose 4 of these people and then give them 4 seats. In how many ways I can do that? Yes?
Exactly the same ways.
Yeah, that's exactly the same. Is that clear? But because, from psychological point of view, we think that we have some priority to chairs, but for mathematics, chairs and humans are just objects, yes? So it doesn't care about that. So it means that you arrange the people and then put chairs on their head. That's exactly how mathematics works. It doesn't matter, yes? So in the other case, you can assume that you have 30 chairs in a row. You actually take a person and put it in one chair, yes? You have 4, okay? But in the other way around, it means that the role of objects and humans are changed here, but that's the same problem. So if you want to say, you can say that, okay, S1 is, if you want to say what is a stage 1 in this new task, you can say that assigning a person to chair 1, yes? But if I ask you how many ways you can do this stage, again you answer 30, yes? Because chair number 1 can be filled up with any one of these people standing, yes? So again, this is 30, and then you can continue. So these 2 problems doesn't have any, so it doesn't, they don't differ from each other actually. That's the answer exactly as the same. So that's one thing I want to mention. Okay. Now we go to the next problem. That is actually a good problem here. How many positive divisors does 48 possess? And how many of these divisors are divisible by 6? Okay, I made this number intentionally small so that we can check it out, but I can ask you how many positive divisors does, for example, 1200 possess? Okay, so because 48 is so small that you can start writing the list and counting it. But for 1200, it becomes harder, and I can immediately ask you about 12,000. Okay, so we want a systematic way to be able to find all positive divisors of that number. Okay, so how we can do that? Yeah, keep right still. So first of all, let me tell you what the problem is. So if you just want to list all of them, if I ask you write all the divisors of 48, but positive ones. So what are the divisors? The first divisor is of course 1. 48 is divisible by 1. 2 is also acceptable because 48 is divisible by 2, and then 3 is also acceptable. 4 is acceptable. 5 is not. 48 is not divisible by 5, but it is divisible by 6. It is divisible by 8. It is divisible by 12. It's divisible by 16. It's divisible by 24. And then at the end, it is divisible by 48. I hope that you agree with me. These are the only numbers so that 48 is divisible by them. Of course, you have also negative ones, but it is mentioned in the problem we are only interested in the positive ones. So this is the list. So if I want to count them, 1, 2, 3, 5, 6, 7, 8, 9, 10. So there are 10. I hope that you agree that, for example, if I write 12,000, this list is probably a very big list. And that is boring if I want to write all of them and start counting them. But we want to solve the problem for this simple case, and then we get a general formula how to count these things. Okay, so what is your opinion about this? So by the way, it seems not related to the product principle, yes, because here if I ask you, give me a divisor of 48, you just, it appears that you write, for example, 12, and then you are done. So there are no stages to this problem. So that's what I'm saying. If you want to use the product principle, you should be able to break it into some parts in your head and then see that how many ways you can do each part and see if the product principle is applicable and then multiply those numbers to get the final answer. Okay? So some tasks are naturally in order so that you can do them in stages. It is clear. For the previous example, I asked you to take these people and put them in the chairs, so it is clear that you can break it into 4 stages. But here I ask you to write the divisors. For example, if I just ask you give me a divisor of 48, you might say 12. It seems that 12 is done in 1 stage. But if we want to do it using the product principle, we have to break it into some stages. So it means that we have to have a smart idea how to do it. Okay? So any opinions here? So that this opinion, this idea can be extended to so that today we can immediately also calculate the divisors of this number. So how should I do that? Think about 48, and I want to find all the divisors of 48 positive ones. Yes?
Do you know do how do you call it prime number factorization?
Yeah, that's a good thing. Okay, I do it. So 48 is 6 times 8, so you can write it as 2 to the power of 4 times 3. Yes? So if I factorize it, so 48, I factor it to prime numbers, I draw a vertical line, then I would say that, okay, 48 is divisible by this prime number. I do division. And then it's also divisible by this prime number. I do the division, do the same thing, but then this one is only divisible by the prime number 3. And mathematicians have already shown that this is always ending with 1. So 1, 2, 3, 4, and then 3. So multiplying them gives me 48. Okay, so then how should I do that? I want to find the divisors. Okay, so how is it related to this one you said? It is related, but how?
Well, those numbers divide 48, so maybe you could somehow get every other divisor from the prime number.
Definitely we can.
I'm not sure how though, I just said.
No, but we can definitely. For example, when I say 6, 6 is also 2 times 3. It is not possible to have another prime number here appearing, yes? Because if it appears, it is not a divisor. When you say it's a divisor, it means that this number should be divisible by this. So this means that the prime numbers that appear in the factorization of this number are definitely only these numbers. It cannot have an extra factor of here, prime factor here. Because for example, if I write 2 times 3 times 5, forget about these names. Do you think this number is divisible by that number? Yes or no? Is this number divisible by that number? No. Yes, because if you put them here, what is the meaning of divisibility? It means that if you divide them, the answer is an integer. Okay, this one and this one are simplified. This one and that one are simplified. So 3 2's are left here, which is 8, and then 1 5 is also left here. So this is a fraction, so it's not divisible. Yes? So if I say that I want a divisor of this is definitely true that I cannot have other prime factors in the factorization of that one, because otherwise it is not divisible. Is that clear? Okay. But, so this is this one. For example, let me look at the other one. For example, 12, 16. What is the factorization of 16? It is just 2 to the power of 4. If I just tell you, is this divisible by 2 to the power 4, you would say yes, because if I write this in the numerator, I write this in the denominator, this and that are cancelled, 3 is left. That's good. And then, for example, let me write 12. So what can I write for 12? I can write 2 to the power of 2 times 3. Yes, because 2 to the power of 2 is 4 times 3 is 12. If I show you this number and this number, if I say you put this in the numerator and you put this in the denominator, because I have 4 2's in the numerator, only 2 2's in the denominator, 2 2 are left, and then 3 by 3 are gone. So that's completely clear. So you see that if I want to now, can you see that this is also a product rule somehow? Can you relate this way of thinking to the product principle? And if yes, how? Can you tell me what is the general form of all these divisors? What are the general forms? I hope that you agree that if D is a divisor of 48, what is the general form of the factorized form of D? If I factorize D, what do you expect to get? D is one of these divisors. If I factorize D, what do you expect to see in general?
2 and 3?
Yes, you see 2, and you see probably 3. For example, you see that here I have 2, 3, here I have 2, 3, here I have 2. But I cannot have more than 2 or 3, yes, as a prime factor. And then, of course, with some power, so let me write alpha, and let me write beta, yes? But there are some limitations for alpha. What are the choices for alpha? What are the possible choices for alpha? This problem is extremely simple, by the way. I want you to write this in your head in the numerator, and I want to write this in your head in the denominator, and see what can you choose for alpha and beta, all possible choices, yes?
Alpha cannot be greater than 4 and beta cannot
So what are the choices? Alpha can be either,
less than or equal to 4.
just name them.
Oh, 1, 2, 3, and 4.
No, it is 0, 1,
Oh.
2, and 3, and 4, yes? Because 0 can be chosen, yes? If I say 0, it means that there are no 2's, yes? That's also acceptable. And what are the choices for beta?
1.
No, I
0.
just told you 0. Either you don't choose, okay? So now you realize that writing a divisor in this way can be seen as a a two-stage task. Yes? What is the stage one? Stage one is choosing alpha. Stage two is choosing beta. So you see, it was not clear it is related to the product principle, but if you think in this way, you realize in order to write a divisor, you are facing two choices. One choice for alpha, one choice for beta. And then how many options are available for alpha? How many options? In 1, the number of options available for alpha is 1, 2, 3, 4, and 5. Yes? And how many options are available for beta? 2. Is this 2 independent of your choice for alpha? Yes. Whatever you have chosen for alpha, and still you have 2 options available for beta. So this means that in this way we connect this problem to the product principle, which is with 2 stages. So this means that the answer to the question mark is 5 times 2. And by the way, we made a mistake. How many did I count? Is it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So there are 10 of them. So that's the way. But I hope that you immediately agree. This is a method that you can immediately increase to other values. For example, if I ask you how many integers, how many positive divisors are in 12,000, how can we answer that?
So we would use prime number
factorization, but I intentionally gave this number in a way that you can do it simply. So because 12,000 means what? Means 12 times 10 to power 3. Yes? But 12 can be factorized to 2 to the power of 2 times 3. And then what is 10? 10 is 2 times 5, factorization of 10 to the power of 3. This becomes 2 to power 3, which becomes 2 to power 5, and then 3 alone, and then 5 to power 3. That's the factorization of 12,000. Yes? Okay. Now, if I ask you count the total number of positive divisors, how do you count them? If I have a divisor of 12,000, can you tell me what is the general form of 12,000 divisor? What is the general form? Yes?
So it would be 6 times.
So just tell me what is the general form first. Yes?
2 to the power of alpha.
2 to the power of alpha.
3 to the power of beta.
Yes?
Times 5 to the power of gamma.
Yeah. Something like this. So this is the divisor, yes? But how many options, as Rocco mentioned, how many options I have available for choosing my alpha? Either I don't choose it at all, or 1, or 2, 3, 4, or at most 5, yes? And then beta, 0 or 1, and then gamma, what? 0, 1, 2, and these are the options, yes? And then, so how many options I have here? 6. Independent of what I choose for alpha, still I have 2 options for beta. Independent of what I choose for alpha and beta, I have 4 options for gamma. So the total number of the positive divisors is what? 6 times 2 times 4, which is 48. And by the way, it's not that easy at all to calculate. So it didn't take me that much time to calculate this perfectly fine, okay? And then I told you that it is good practice to write a computer code to generate and count them, yes? Okay, is that clear? Okay, so for example, now do you remember there was something else in the question? How many of these divisors are divisible by 6? Yes? In the case of 48. For example, I can say in this problem, how many divisors are divisible by 100? Or something like that. So how do you think I will answer that? How this will affect my problem? Now here, I was interested in all the divisors, but now not all of the divisors are divisible by 6. For example, 16 is a divisor of 48, but itself is not divisible by 6. So I have to rule it out. Now, in the second part of the problem, I am only interested in those ones which are also divisible by 6. It is a very simple task, by the way, so I have to rule this out, this out, this out, this out. This is one of the possible values because this is also divisible by 6. This is also divisible by 6. This is also divisible by 6, and that is the one. So how many of them are there? 6, 1, 2, and 3, and 4. Yes? But of course, this is so simple to write the list and count, but we want to find a systematic way. So now, can you tell me the same problem? This time, I am not interested in all the divisors. I am interested in all the divisors that are also divisible by 6. How this will affect my choices of alpha and beta? Because I want to have, so on the one hand, this divided by 2 alpha times 3 beta should be an integer. On the other hand, 2 alpha times 3 beta divided by 6 should also be an integer. In the first part, I had only this constraint to satisfy. I wanted this number be divisible by that number. So I chose alpha from 0 to 4, and I chose beta from 0 to 1. But this is not the only constraint now. The second constraint is that this number, whatever it is, should also be divisible by 6. So I have some more constraints to satisfy. So how this will affect my choices of alpha and beta? For example, can I choose alpha still 0? No, because if I choose alpha 0, there is no 2's in the numerator. But at least there is a 2 here, because 6 is 2 times 3. And then, even if the 3 part cancel with that part, this 2 is left in the denominator, which is not an integer. So it means that, yes, here I cannot choose alpha to be 0. Yes? Is that understandable? Alpha cannot be 0. Because if alpha is 0, there is no 2 in the numerator that can cancel out with the 2 in the denominator. Can beta be 0? No, because there is a 3 in the denominator. So beta cannot be 0. Okay, how many choices I have for alpha? Not 5 anymore. I have 4 options. But how many choices I have for beta? Only 1. Yes, and that the question mark is not 5 times 2, it's 4 times 1. And the answer, as we predicted, is just 4. Okay, let me ask the same question here for 12,000. How many of these divisors themselves are divisible by 100? So this time I am interested in all the divisors of this number which themselves are also divisible by 100. So how do you think it will change the number of choices that I have for alpha and beta? So this is for the new problem. So alpha, beta, and gamma. Okay. If you answer this question, it means that you understand what I said. Okay. So how many choices I have for alpha now? How many? So you don't need to just give me a number, tell me how to calculate. The divisors of 12,000 have this form, yes? In the previous problem, we had this constraint that 12,000, this should be an integer. That was the previous problem. But we factorized 12,000, we got that one. So this means 2 to the power of 5 times 3 times 5 to the power of 3 is divided by d. And then we have d of this form. So it is 2 alpha times 3 beta and times 5 to the power of gamma. we want to choose alpha, beta, and gamma so that this and that can be simplified to an integer. So this means that alpha is at most 5, beta is at most 1, gamma is at most 3. That is the list that I wrote here. But now in the new setup, I have another constraint. I have this constraint because still I want to have this a divisor of that, or and another condition is that this number itself should be divisible by what? By 100. That's another constraint. Okay, so I want to have this one. But 100 is what? 100 is 10 to power 2. 10 is 2 times 5. So this becomes 2 to power 2, 5 to power 2. That's 100. Okay, so then I have to choose, I have to put this one here. So do you see that I have also something to care about here, because alpha, can alpha be 0, for example? If alpha is 0, it means 2 is gone, but still there are some 2's left here. There is no way for such a number to be an integer. So there should be a limitation for alpha again. So alpha should be at least 2, not less than 2. So this means that alpha in this new scenario starts from 2. And the number of choices that I have here is no longer 6, is 4. And then, do you think this will affect the number of choices for beta?
No.
No, because beta, there is an extra 3 here. There is no 3 here, so I should be worried. So beta is still the same. But how many gammas I have? I cannot choose 0 because I have 2 powers of 5 to take care of. I cannot choose 1, but I can choose 2 or 3. So it means that how many options are available? 2. Yes? So this means the question mark for this part is this times that, which is 16. Okay, so it means that if you list all the divisors of this one, we get 48, but only a third of them, 16 of them, are also divisible by 100. Is that clear? Is that clear or not? Okay. Okay, so I think I end the lesson here. The next part is actually the sum principle, which is also a very simple thing. But I mean, multiplication and addition, things like that are very trivial. So I have 3 pens, you have 5 pens, how many pens we have? That's a very primary school task. But believe me or not, especially after when I finish teaching you the sum principle, then you will get confused sometimes. Okay, am I allowed to use the sum rule here, or am I allowed to use the product rule? Some people actually mix things up. This is quite common. Okay, I will stop here, and then this will be the topic that will continue on Friday. Any questions? Okay, thank you.
Thank you.